All right, so this is going to be tutorial, as you can see from the talk, from the title. So after many years, I actually had the opportunity to teach a course on detection estimation, something that is offered in most electrical engineering courses, electrical engineering departments. So I'm actually writing a book on information theory, and this is actually going to be part of one of the parts of the book. The statistical inference part. So if you look in the typical courses that you find detection estimation, they use this kind of books. And if you look at the table of contents, you find elements of hypothesis testing. The match filter plays a very important role. Kramer-Rao, and then a Wiener and Kalman play a very important role, and also continuous time. So actually it's very interesting because there is really no information theory in any of these standard courses. And it's interesting because the information theory community was very late in adopting things like, for example, the relative entropy. Okay, so in fact, I went to Shannon's archives in the Library of Congress, and he even keeps the letter that he got from Kullback, sending him a paper, a preprint of his paper with the Kullback-Leibler divergence. But he never used it, and other famous information theorists, as Gallagher, for example, never used relative entropy. So it was pretty late in the game. Blayhood and Chisar, perhaps some of the Russians realized how important that was. So interestingly, one of the pioneers in detection estimation was Shannon himself. In fact, in 1944, he didn't publish this. This was just a technical memorandum in Bell Labs. He actually came up with the derivation of the optimality of the match filter. But unlike what North and Middleton had done right about that time, in which they just showed that the match filter was the solution of a maximal signal-to-noise ratio problem, he actually showed that it was the solution to a minimum probability of error problem. Not only that, he did it in colored noise. So this is really the beginning of communication theory, is this technical memorandum here. All right, so this is the structure of the course: information measures, sufficient statistics, binary hypothesis testing, M-ary hypothesis testing, which is very important for us, and then estimation. So what you need to know about information measures, so this is just the notation, and then you're going to see this quite a bit in the talk. The logarithm of the Radon-Nikodym derivative between P and Q, I'm going to denote as this. That's what we call the relative information. And of course, the expectation of that with respect to P is the relative entropy, but very important for what I'm doing, it's not just the expectation of that random variable, but its distribution. Okay, so the CDF of the relative information, sometimes we call that the relative information spectrum. Okay, in the special case where you have a conditional distribution and unconditional distribution, then we call that the information density. Of course, the expectation is the mutual information. All right, so the first person to deal with big data was Fisher, and he was interested from going from big data to not so big data. So he came up with the concept of sufficient statistic, and when he described it, he has the word information there. So there must be some relationship with information theory, and in fact, if you look at Cover and Thomas in their first chapter, you already find a section on sufficient statistics, and they define it as a function of the data such that the mutual information is preserved after you take that function. Mutual information from the unknown parameter to the observables is the same as from the unknown parameter to the statistic. Now, of course, the parameter, when you define sufficient statistics, need not have a distribution. So this is actually true for all possible distributions on theta. Okay, so it's kind of like saying, well, all Bayesian forms of the problem will satisfy that property. Oops, I don't know what I did now. Okay, so this is something that, in fact, you see throughout the statistical inference literature and also signal processing, and this drives me crazy, the observations they denote as X, and that's not. That's something, that's something you should never do. So the observations are Y, okay? This is the yucky stuff with noise, and then this is the statistic, the thing that then you go from big data to small data. All right.
The X camp versus the Y camp.
Huh?
The X camp.
Yeah. So we are winning.
Y camp.
All right. So the official definition is that when any residual randomness in this C is not going to, any residual randomness in Y, once you know Z, is not going to be due to the unknown parameter. All right, but information theoretically, you can either do it like Cover and Thomas, or in fact, you can show that you have this property that in fact the information density that I defined before is preserved from V to Y and from V to C. And this is non-Bayesian. You don't need a distribution on V to be able to define this. All you need is really a reference measure for Y. It's an auxiliary reference measure that dominates the whole class of possible models. If there is no such thing that dominates everything, then you are in bad shape. So this is actually much nicer than the usual factorization theorem, which is only applicable to deterministic sufficient statistics. But in fact, in practice, you may actually have situations where you have random statistics. So, for example, you may have a sampler, and that sampler may have an offset, but yet, if you sample at the Nyquist rate, you're going to have sufficiency. All right, so in the case of a binary parameter, so the model only consists of the two distributions, then this boils down to the information density, the relative information, with the data being the same as the relative information with the statistic. And then if the relative entropy at the statistics is finite, then you might as well use this easier condition where the data processing is satisfied with equality. But if it's not finite, the fact that this is infinite equals infinite, then that does not imply that you have sufficient statistics. So this is more general. All right. So now let's go to hypothesis testing. Binary hypothesis testing. Traditionally, this is the kind of terminology that is used. Null hypothesis, alternative hypothesis. You have a hunch, and then if your experiment validates your hunch, then you can go ahead and publish it. And that's, if so H1 is true, you call that the alternative hypothesis. And then you have all these kind of names for going from one hypothesis to the other, depending on the application. So I don't like to use any of that terminology, because for us in communications, H0 and H1 are on equal footing. Okay, usually it's like a bit. It's either 0 or 1. So there is no alternative and no null. They are both equal. So the only thing we have to remember is pi 0 given 1, probability of deciding 0 given that H1 is true, and vice versa. So I don't use that terminology. And in fact, I'm tempted not to use the terminology of hypothesis testing. Maybe decisions should be better. But I chickened out, and I in fact, continue using hypothesis testing, not to be too contrarian. All right, so here the fundamental trade-off then is the region that you can achieve between the two error probabilities, and that's the lower envelope. So that's where the action is. Now, you know, of course, all the asymptotic results, the large deviation result, Chernoff-Stein lemma, and when both probabilities go to zero exponentially and so on. We do that in the class, but as always, what I do is present the results in what I call the single shot mode. So we're always assuming that we have just one quantity that is not necessarily multidimensional, does not necessarily have an infinite dimensionality that goes to infinity. Then we get bounds, upper and lower bounds on that, and then once we have that, then it's pretty easy then to get the asymptotics. So what I'm going to show you here is a selection of the bounds, of the achievability and converse bounds. Okay? So first of all, let me just say that by going to the Bayesian case, then you have a very nice kind of operational characterization for this relative information is the added evidence in favor of one hypothesis versus the other once you see the observations. All right, so then this is actually, this bound is implicit in a paper by Walt in 1945. Even though he was using relative entropy, he didn't know he was using relative entropy, but that actually predates Kullback and Leibler. And that's just the data processing inequality. So that's a pretty powerful achievability result. Excuse me, a converse result. Another converse result you can get just simply by change of measure. And notice that now we already have the distribution of the relative information. Now this one is something that you haven't seen, and it's a cute result that I got by distilling kind of like the key idea in Shannon, Gallagher, and Berlekamp, which is a very famous paper in information theory. It's actually the last paper that Shannon wrote, or that Shannon was a co-author of. All right, so then the only thing I need to tell you here is that what P alpha is. All right, so we have P0 and P1, and then P alpha is the tilted version. So it's the one that you get by taking a convex combination of the relative informations, and then you normalize it so that it's a distribution. Okay, and the normalization then involves the Rényi divergence. Okay, so this, of course, is instrumental. This converse is instrumental later when you go to the asymptotic paradigm to, as we will see later, to give you the actual result that tells you how fast you can have both error probabilities go to zero exponentially fast. Now, as far as achievability, the interesting thing is that in contrast to most problems in Shannon theory, in this one, we have actually a constructive method that actually we know what the optimal rule, because that's a name and person rule. Okay, so that's a luxury that we have, and that certainly makes the analysis a lot easier. This one is very simple. Again, involves some very simple change of measure argument. Now this one, what happens here is then the achievability result, again here, the non-asymptotic achievability result is very simple. You just have a deterministic threshold test and a change of measure. And then using that converse that I showed you before, that I said was distilled from Shannon, Gallagher, and Berlekamp, that's when you can show that these things are asymptotically tight once you take the logarithm and you normalize by 1/n. All right, so now, M-ary hypothesis testing. So for us, this is fundamental, right? Because this is all about decoding. When you have an error control system, you have to decide between one among several messages. And so this is actually, for us, completely fundamental in digital communications. Statisticians, you don't see a lot, you take a book on hypothesis testing, you're not going to see a lot of M-ary hypothesis testing. The one case where they are really interested in doing that is in non-parametric estimation, where there is this trick to get a lower bound. We have a space of possible parameters, and I think this is due to Ibrahimov and Hasminsky. So the idea here is that you have a genie that tells you, well, actually, I'll tell you that the true one belongs to a finite class, and then if this finite class, you have a minimum distance between the errors, the distortions of this minimum class, then you can lower bound the average distortion by the minimum distance times the probability of error for an M-ary hypothesis testing problem. So that's why then in statistics some of our beloved converse bounds, like Fanos inequality, have been used. And Binyu has written a nice paper on several methods that are popular in that respect. All right, so what about achievability? What kind of bounds can we find for achievability here? And I'm only going to show you the Bayesian case because we don't have much time. So as you can see, every time I've shown you a bound so far, the bound either had relative entropy or relative information. Now we have conditional entropy. So remember, this is the error probability. Now Bayesian error probability. So we have a distribution on V, and that result is kind of like an old result. And the way you prove this is by first considering the blind case, so where you don't have any observations. So then you have that, and then you condition on one observation, and then you take the average. So this is actually a special case of this other theorem. This is not new, even though the form in which I express it here is new. And this actually goes back to the 1960s, a paper by Tebe and Dwyer. Now this one is quite easy to prove. And in fact, what you need to do in order to prove this result is exactly what you need to do in order to prove Shannon's achievability result for channel coding, where essentially you say, well, let me look at the likelihood once I have the observation, and let me put a threshold rather than having an optimum rule that selects the maximum. You put a threshold. If there is no one above threshold or more than one, then you say, okay, I give up. All right. So the only difference between this result and Shannon's theorem is that here you don't need to use random coding. Okay, because the optimal decision rule is known. So that's a pretty powerful. The only thing here I didn't define, maybe I should have defined at the beginning, this is the information function. Okay, so this is just the logarithm of the reciprocal of the probability. All right, so now let's go to converses. All right, so the converses, of course, the first one is Fanos inequality. So now here we just turn it around. Usually we upper bound the conditional entropy. Now we have it in the other way around. Now Shannon, for some reason, never liked to use Fanos inequality. He came up with his own inequality, and which is harder to prove, and essentially, for the purposes of asymptotic theorems and so on, is as powerful as Fano. Now here, we came up with this converse for minimum error probability. And in fact, this beats the other converse I showed you most of the time. And in fact, generalizes this converse I had with Han. And notice that the beauty of this is that it's kind of like a dual of the achievability result. Because the achievability result had here less than or equal an infimum, and then had plus and plus here. Okay? Wow. So, you know, that's nice. And then, in fact, this is all these things are special cases of the meta-converse that Yuri Polyansky had in his thesis. And in fact, this meta-converse, what you do here is you introduce a an auxiliary distribution, and then depending on how clever you are in finding that auxiliary distribution, then you can get pretty tight results. And in fact, it has been shown recently that by being very clever, then you can find actually equality in that meta-converse. The only problem with this, it sounds like nirvana, because here you have equality, so you don't really need to worry about bounds anymore. The only problem is that the auxiliary distribution, in fact, when you compute it, the normalizing constant is as hard to compute as this. Okay, that conceptually is nice to know that the meta-converse can be tight. All right, so I think I don't have a lot of time left, but as far as estimation, I put most of the emphasis on Bayesian estimation, but I do like to show, like, for example, the Kramer-Rao bound, which is called the information inequality sometimes. It's actually cleaner to do it in this way, Hammersley-Chapman-Robbins, where, in fact, this has a very simple proof. This is completely general, and this is in the case of unbiased. And this guy here is the Pearson divergence. Okay, so that's a special case of an F divergence. And then you can recover, this is stronger than Kramer-Rao, you can recover Kramer-Rao. And the way I like to define Fisher's information is not the standard way, but the way I like to do it is by taking the derivative of the relative entropy. Of course, Kuhlbach and Leibler already noticed that you had that property in the paper where they introduce the relative entropy. Okay, but it's much nicer to give the definition in this way, which is much more kind of intuitive, and then show the standard thing with the partial derivatives and so on as a result. Okay, and then in Bayesian estimation, the MMSE, then I show the Bayesian Kramer-Rao bound, or the Van Trees inequality. And then, of course, these guys are the conditional Fisher's information, and the unconditional one, this is the original one due to Fisher, which just shows you if you get a carbon copy of your density and you move it a little bit, how different it is from the original one, so that you can put as a special case of the general one. Now, particularly interesting here is the case where the observations are contaminated by additive Gaussian noise. And in that case, the MMSE, as a function of the distribution of the unknown quantity and the signal-to-noise ratio, so we use that notation, MMSE x alpha, and that, of course, has turned out to have very important connections with information theory that we discovered a few years ago. But before I show you that, since it's an electrical engineering course, then it's nice to show some circuits. So that's the most elementary estimator that you can find in the world. Then if you have, rather than random variables, you have stationary processes, then these resistors now become transfer functions, and then you have the non-causal Wiener filter. I don't do causal Wiener filtering, which is a waste of time. And I do the Kalman filter, but just because I have to. And then you see, then there are all these, but Marcelo doesn't want me to continue, so I'll just show you the main thing. And the main surprising thing is that, in fact, if you integrate this guy, this MMSE, over all signal-to-noise ratios, if you have never seen this is really cool, then you get the entropy. Okay, so you have the world of Wiener and all these people, Gauss and so on, and the world of Shannon on that side. Okay, so that's a special case of that formula. All right, so I know that many of you came because of this. So this This picture, I'm here eating jamón ibérico, which is one of the most delectable things in life, although some people, because of religious superstitions, refuse to take it. All right, so how do you look in miniskirt and red platform boots? So there I am. Okay, this is me. Okay. 16 years old. And yeah, so in fact, my legs are pretty much the same still. Okay, thank you.
So questions while we get ready for the next speaker.
Sergio,
Yeah.
so this workshop, and I'm glad to see that you're doing this hypothesis thing again. And so this is a workshop on big data, and I've been reading some papers. They all look at precision and recall. You want to say something about it?
I have no idea. I mean, I recall.
PR
Huh?
Look at any data. I mean, they do inference, big data papers. They all talk about PR curves, precision recall.
That shows you how little I've read of that literature, because
It shows it's a completely different world altogether. And
so what's the punchline?
I'm asking whether you would want to include what precision recall means in this language. From a
I don't even know. I mean, I know recall. There was some recall in California for the governor.